So we have here today another physics problem, this one about Gauss's law, probably one of the most important concepts and topics in electromagnetism. We're given that a non-uniform but spherically symmetric distribution of charge has a charge density of rho as a function of r, given as follows, where this is the charge density inside the sphere, r, less than or equal to big R, which is the radius of the actual sphere, and r is some point that we choose. And they tell us that there's no charge outside of the sphere, which is very important which is a very important piece of information. Where rho sub 0 is a constant, 3q divided by pi r cubed. And so let's draw that before we go any further. So we have here a sphere. Hopefully that looks something. I'm trying to make it three-dimensional here. And here's our radius of big R. So the first part of the problem, part A, is asking us to show that the total charge contained in the charge distribution is Q. And you may remember that the charge density, rho, which is just the Greek symbol, is equal to the charge of an object, Q, divided by its volume. And if we had a uniform charge density, we would be able just to multiply this density by the volume, and we would be left with just the charge, because the volumes would cancel. But that's not the case in this problem. We have a non-uniform charge density given by this function right here. So therefore, we're going to have to use calculus in order to find the charge. And so if we look at it like this, say we take the charge density function that we have, rho of r, and we multiply it by some infinitesimally small element of this volume. We'll call that dV. And we multiply, and we'll have the charge of some infinitesimally small area of the volume. So if we take that infinitesimally small charge of this volume and we integrate it with respect to that volume entirely, we should be left with the entire enclosed charge of this volume. So therefore, what is this expression basically equal to? Essentially, what this is the rho of r, which we have. We can put that outside the integral. Put that right there. Rho of r, because rho of sub 0, is just a constant, multiplied by 1 minus little r, which is some point that we choose, divided by big R, which is the radius of the sphere, and is therefore constant, multiplied by some elemental piece of the volume, which that elemental piece is basically, make believe this was an orange and we were peeling off just surface areas of this sphere. And those surface areas are just going to be the surface area of a sphere, and the formula for that is 4 pi r squared. And so if we integrate some surface area of this volume by the density function, we'll get the charge of one layer of the sphere. And if we integrate this from the center of the sphere all the way to the end of the sphere, which is going to be of radius r, we integrate it with respect to r, we'll be left with the charge. And so that's what part A is all about. It's all about making an integration and then showing that the charge is equal to Q. So we just basically, they told us that the enclosed charge is Q. We just have to prove it, and we'll prove it by the integration here. And it turns out to be a very trivial integration, which you should be able to work out. You can pull out all your constants out, and you'll see it's basically just an integration from 0 to r of r squared minus r cubed divided by big R, which is just a constant, of course, and of course that's a very trivial integration. It'll be just rho naught 4 pi multiplied by big R cubed divided by 3 minus r big R cubed, to the fourth divided by 4r, and when you evaluate at 0, of course, it's just going to go away. And so at this point, we can plug in the constant rho sub 0, which was just equal to 3q divided by pi over r cubed, pi times big R cubed times 4 pi, and you'll start realizing a lot of terms will start canceling out. R cubed minus divided by 3 minus r cubed, see those r's will cancel, r cubed divided by 4. And so going one step further, hopefully you'll realize that there's 2 r cubes here. If we pull both of these r cubes out, they will cancel with this r cubed, and these 2 pi's will cancel out. And so we'll be left with 4 times 3, 12q times 1 over 3 minus 1 over 4, which of course is just 1 over 12, and obviously 12 times 1 over 12 is just 1. And we're left with exactly what the book claimed, which was that the total enclosed charge was Q. So it's just a lot of algebra and simplification to prove one point. And obviously that had absolutely nothing to do with Gauss's law, but this next part, I believe, does have something to do with Gauss's law. Part B says, show that the electric field in the region R greater than or equal to R, or basically outside the sphere, is identical to that produced by a single point charge with a magnitude of Q at the very center, that is placed at R equals 0. And so basically, we have to use Gauss's law in order to find the electric field. How do we know that we can use Gauss's law, though? It's because we have because one of the rules that holds for Gauss's law is that there has to be geometric symmetry, and it's stated in the problem that we have a charge which is spherically symmetric. And so the first step is to write Gauss's law in its most general form. So let's do that. Gauss's law tells us that the closed loop integral of the electric field dotted with an elemental surface area is equal to a charge enclosed divided by epsilon naught. And what is this actually saying? This is actually just electric flux. And what is electric flux exactly? Well, by definition, electric flux is the electric field multiplied by the unit by the unit area. We should create something in which the electric field is propagating. We should create a surface in which the electric field can propagate towards to. And so the electric field is going outwards, going radially outwards. So the best choice of a Gaussian surface, is what they're called, is to choose a spherical one because it'll be symmetric throughout. So we draw that. That is our imaginary Gaussian surface, and it has a radius of little r, our arbitrary r. And if we find the amount of flux the amount of electric field going through this Gaussian surface, it'll always be equal to the charge enclosed divided by epsilon naught. And so we can evaluate this, and we can say exactly that the electric field is going to be constant because it's just a charge that is enclosed, and we have to integrate the elemental surface area, which is basically just after we integrate a small elemental piece of the surface area, it's just going to come out with the entire surface area of a sphere, because that's what our Gaussian surface is. It's a sphere. So that our surface area is just going to be 4 pi r squared. The surface area of a sphere equal to Q enclosed divided by epsilon naught, and then you'll see that our electric field is equal to just our Q enclosed, which we found in the last problem turned out to be Q, divided by the area, 4 pi r squared epsilon naught, which you'll probably recognize as being very similar to the standard definition of electric field. Some constant, 1 divided by 4 pi epsilon naught, times a charge divided by its distance squared. And so the problem asked us to compare two electric fields. The other electric field being a point charge with a magnitude of q. And we can do the same thing we did up here. We can choose a Gaussian surface in which the electric field will propagate radially outwards, and that Gaussian surface that we should choose will be the same as before, which is just going to be the surface area of a sphere, and make believe that is a perfect circle. And that's also going to have a radius of little r, arbitrary distance. And so we can say up here, we're going to have the same exact thing basically. We're just going to have the electric field times the element times the same exact surface area with an arbitrary r equal to q enclosed. And the q will be the same exact thing because we were told that this magnitude of this point charge is in fact q. Divided by epsilon naught, and you'll notice that the electric field will be equal to the same exact expression as above. And the problem asked us to show that they were identical, and they are in fact identical. Squared epsilon naught.